Thank you very much for the introduction. I'm very aware that this talk is what stands between you guys and a beer out in the sunshine, so I will try and make sure that what I tell you is worthwhile and finished on time, as my two objectives so far. What I'm going to do today is tell you, first of all, introduce Ellexus, for those of you who don't know who we are already. I'm then going to talk about a particular customer case study that we had where they were delivering I/O profiling throughout their continuous delivery framework and implemented something which we call I/O profiling as a service in order to solve some of the problems they were seeing. I'll also round it off by pulling in some information about a few other customer case studies that I think are particularly interesting, and then kind of round it off with a bit about what we learned through the experience, because it was a particularly interesting customer case study, and we were learning through the journey with them. So, first of all, to introduce Ellexus, we're based in Cambridge. I founded the company about 8 years ago now. Actually, my background is semiconductor design, and I became very frustrated with the amount of time spent trying to work out why semiconductor design applications wouldn't work. You typically have very complicated scripted environments, and I wanted to spend a lot of my time doing chip design, but spent almost all of my time doing DevOps and trying to work out why stuff wasn't being deployed properly, why we were having all these problems, and in time started to see that as a much more challenging and interesting problem. So Ellexus was founded to do that, and over time we started to not just look at the way applications access, not just what data applications access from a kind of deployment point of view, but also look at how they're accessing that data for performance and reliability as well. And we work in really any industry where there's big compute meets big data. We occasionally work on very small applications with very specific I/O needs, but in general, we work with applications with very large data sets, and that of course includes the semiconductor industry, life sciences, finance, oil and gas, and so on, as well as other emerging areas such as machine learning. Some of those applications, not all of those applications, some of them are small data sets, but some of them have got quite extraordinarily huge data sets and pose really interesting scalability problems in deployment. Why care about I/O? I suggest that all of you who've chosen to come to this talk at least care a little bit about I/O. But essentially, bad I/O is costing you money. Accessing files, networks, databases, and so on inefficiently costs you money. You can harm shared storage or shared resources by with what we call the noisy neighbor problem, where one user or one application overloads that shared resource with bad I/O. Even if you're not using a shared resource, you're limiting application performance, and if you're using cloud resources, that is obviously a direct cost to you. In-house, it's more about wasting that capital expenditure, whereas in the cloud, you can very easily rack up enormous costs by getting your storage and I/O wrong. So, and just to kind of visit what I've said at the bottom, I/O gets worse when moving to new compute environments, such as the cloud. That's not strictly true. It doesn't always get worse, but quite often what we see is when you change the environment, that's when the I/O problems start to appear. That doesn't have to be when moving to the cloud. It can be any sort of change. So one of our customers actually, they started having I/O problems when they increased the amount of memory on their compute cluster. They were using enormous compute resources in-house. They realized they were memory bound. They spent a lot of money on increasing the amount of memory on their compute clusters, and that immediately alleviated one bottleneck to create another. And so the day that they installed all that memory, the storage crashed completely. And at that point, they realized that they should really start caring a lot more about the way they're accessing their data, because it was through essentially a lazy attitude to their I/O that had masked this problem. And of course, it's much harder to fix the longer you leave it. So this is an example of a problem application with bad I/O, and it really highlights a lot of people have got misconceptions about what bad I/O is, and this is a software build. Software builds are almost always I/O intensive. So if you're doing large software builds and you don't think you've got a lot of I/O, then quite frankly you're wrong. This is just a plain software build. It's supposed to store all of its temporary files on local storage /temp. This is normally run on compute nodes with plenty of local storage. There's no excuse not to use it. But actually, this has been set up to store almost all of its data on ARM Scratch, which is shared storage. It's very expensive shared storage, and whenever this software build is run, you see a noticeable slowdown on the other applications that have to use Scratch. So very, very simple mistake, very, very easy to fix, and relatively easy to find as once you start looking at I/O and once you start tracking dependencies. So the graph that I just showed you was one gathered with one of our tools. I'm just going to quickly introduce them now because it's what we've used to do to gather quite a lot of the data I'm going to show you today. But I won't go into too much detail, and I'll do a sort of a roundup of tools and open source projects as well that you can get your hands on at the end. So the tool that I just showed you is a product range we've got called Breeze. That's for doing very, very detailed analysis of single applications. And it's really, from a usability point of view, it can be used in two modes. You can either use it very, very simply to check dependencies and check that you're not doing anything really badly wrong with a really simple report, or you can delve in a lot more detail, and that's what some of our more expert users do when they're trying to do more detailed optimization. From a system monitoring point of view or monitoring at scale, that's where you would use Mistral. It doesn't collect anything like the kind of detail that Breeze does. As with any kind of monitoring, you've really got to choose between detail and scalability, and Mistral lets you do that. But once you see kind of how it's deployed, I think that will become a bit more clear. So we've kind of pulled out just some best practices. These are things that we try and roll out for our customers. Obviously, the implementation depends on the problem, but these are some of the high-level best practices that we try and start from. The main thing that we want to achieve is that applications are fast, agile, and cloud-ready. Those are the things we're trying to achieve. Everyone needs fast, even if you're not worried about performance. Fast generally means cheap. It generally means that you can you can get things done. Obviously if you're running continuous services, potentially it means we need to kind of widen the definition of fast to mean slim, so that you can run those continuous services on lighter resources. But ultimately, usually when it comes to I/O is the bottleneck if you're doing any significant amount of it. And Moore's law isn't working for I/O. We can't rely on, although we can rely on computers getting faster and storage getting faster, storage is not getting faster at quite the same rate as compute. So to put this into perspective, a single memory operation in the early 90s would have taken 1 or 2 compute cycles to complete. Now, on this machine in front of me, it will take many, many thousands of compute cycles to access memory. And the memory has got a lot faster, but the compute has got so much faster. It's now hugely costly to do any kind of I/O operation. And that's even just accessing memory. That's not about accessing disk. That's not about accessing remote storage. So you've really, really got to make sure that every single one of those IOPS count. And you do that by optimization and good design. Optimization doesn't have to be hard, as we saw in that first example. Optimization can just be about defining a sensible framework and checking that you're actually following it. By agile, I'm not talking about agile methodologies. I'm talking about the ability to move your infrastructure to make sure that you've got a really good handle on what all the dependencies are, making sure that you don't have some legacy script that nobody knows what it points at. Just making sure that you're ready to do that lift and shift, and you don't have any bad I/O patterns kind of hidden in there that's going to suddenly fall over when you move to a new platform. And for those of you doing significant amount of I/O, really thinking about being cloud ready, not just from a point of view of being able to get there if you decide to move on-prem into the cloud, but also making sure that your storage sizing is correct. So what we see a lot of the time is people overestimating their storage needs rather than underestimating. They might look at the peak I/O performance or requirements of a particular resource. Now, if that's a hard requirement, then you're going to have to provision for that peak need. If you can make do with having your service running or your application running slowly during that time, you can actually choose a much, much cheaper type of storage with much lower I/O capabilities and make significant costs to your storage. So to put that in perspective, one of the cloud vendors that we work with reckon that for I/O intensive applications, people are typically spending twice what they need to at the moment by over-provisioning their storage. And where does this bad I/O come from? Could be from legacy code. A lot of code was written a long time ago where the only I/O was to a disk that was really fast and local. Bad I/O can come from third-party tools and libraries. You don't necessarily know from one version to a next what the I/O implementation is going to be for those libraries. Bad I/O comes from misunderstandings about IT infrastructure, like that example I just showed you first of all, where the developer didn't realize they were supposed to use local storage. And bad I/O can come from changes in your working environment, such as increasing the amount of memory, or simply bad code and lazy design. So here is the case study. The customer in question, they make software that's very I/O intensive, distributed software on their own compute cluster, which is in-house. They run unit tests, regression tests. They run applications under development. They run their software builds, and they often build new workflows and new applications built on legacy code. So quite often there'll be an I/O problem for an application. It can take a long time to track that down, and that problem can reappear because the base code that it was used from is still hanging around somewhere. So working out the provenance of their applications and the dependencies is really important. The architecture, so they've got something called a host leaf architecture, where they have different compute nodes. Essentially, they've not spent enough on their network in order to have the same kind of connectivity from all of their compute nodes to their storage. So what they've done instead is they've bought a small amount of very expensive high-speed network to go from these host nodes. Most of the compute is done on a leaf node. The data is aggregated on the host node and then sent to the storage that way. And that actually is really it's a really cost-effective way of getting really good performance from very expensive shared storage. They've got around I think 7 petabytes of storage. So that on high-speed spectrum scale storage is pretty expensive. And this goes wrong in a number of ways. So first of all, users aren't supposed to write to the shared storage from the leaf nodes, but of course they do. And if they, although I've only got 4 leaf nodes there, you can easily have 100 compute nodes all hammering the storage, and that's more than enough to make it fall over because the network just simply can't keep up. The network can't keep the files in sync. And the next thing that they can do very easily is run applications with the debug flag left on. If this is done at scale, it can generate so much data so that even if they're doing it in the way they're supposed to from the host nodes, it can still cause the storage to fall over. And well, I think I didn't put a slide out for this. The third thing that they do is delete files all at once in parallel, which again can cause their file system to fall over. It's a particular problem with the architecture that they've got. And they know about that, but until they came to us, they had no way of measuring that. So what we did was we deployed Mistral, our tool for running in production, on all of their applications. It's designed to generate an alert if the application does any of the bad things. So if leaf nodes write to the file system at all, or if host nodes write to the file system at all, too much. And the thing that they were looking for is the sort of two use cases. One is my house is on fire, as in I'm sat there looking at all the monitoring screens and something really, really bad is happening. The other use case is, okay, I've come in Monday morning, something went really badly wrong with the compute cluster over the weekend. I missed it, and I need to look historically and find out what's going on and make sure that it doesn't happen again. So we set up Mistral, first of all, with contracts. We call them, the config files are called contracts, to monitor those things. And we logged all of that data to I believe it was an Elasticsearch database, so that all of that data could be viewed with Grafana. If you haven't tried it already, I recommend giving it a go. It's a really, really fantastic tool for looking at both the now and the historic data. So this is what the contract looks like. It's pretty simple. You decide how often you want data. So I've chosen every 60 seconds. You've got 3 rules with a human readable name down the side. The path or mount point that you want to monitor. What you want to monitor, so reads and writes. And the first 2, and then creates and deletes is the third case that was causing them a lot of problems. And this is just monitoring one part of the whole file system. They in fact had kind of a bit more subtlety in their contracts. There's different areas of the file system they wanted to monitor. but this illustrates kind of how you set that up. And they had different limits for the host nodes and the leaf nodes. And this is a kind of alert that you see when you get it in a kind of plain text. So you get the time, the rule, what actually happened, so how much data was actually logged, the process ID of the application that caused most of that I/O to happen, the program, the last file that it accessed, and the job ID. You can also configure it to give you a stack trace and all sorts of things. The job ID ties it to the host compute node and all sorts of other metrics there. The PID will tie it to other metrics that they've got running, monitoring CPU and memory and things like that. The program tells them which application has caused the problem, and the file, the last file that it accessed. It's just a sample, but it's usually pretty accurate in terms of if they're hammering the storage, the last file they accessed is probably the one to look at. And this is pretty good, just as a start. We almost completely eliminated rogue applications after 12 months of running this. So they put in not just the ability to monitor, but also the business practices in place to actually go back to their developers and give them information about what was going on. So give them those lines of the log file so that they could actually hone in on what the problem was. And that was really good for kind of cleaning up their system, but actually the next step is to prevent problems from reoccurring, and that's where the I/O profiling as a service and the good practices when it comes to putting in place a quality assurance framework in their continuous delivery was really, really important. So the quality assurance framework was really important in making sure that none of these problems reoccurred. And the I/O profiling as a service was a way of users or developers getting more information about their tools so that they had a really simple way of getting I/O information about the product that they were working on. So the best practices to set this up. Obviously, the specific problems for this use case are not necessarily going to translate at all for your organization. So you need to find out what is normal. So first of all, put some monitoring in place like they did in order to find if you do have a house on fire situation, find out what's going on there and fix it. But secondly, find out what is normal. The next thing you need to do is check that normal is good. Quite often when people do things just simply look at a list of dependencies of their application, they spot problems there, libraries that they shouldn't be using and things like that. So check that normal is good and fix it. And then finally put in the test frameworks to prevent regression. And the things to look for are very, very simply, is the data in the right place? You do not have to be a performance expert to look at that. Are you getting the right version of libraries? Quite often, if you've switched to a new version of a particular library, some parts of your framework will be using that, other parts will have been forgotten. If you haven't actually automatically got a list of dependencies that grabs everything that you're touching, then you may well forget that. You want to look at where you're storing temporary files, making sure that's fast local storage. You want to look at hard-coded paths. I'm sure we're all guilty at some point of hacking something in our home directory and then accidentally letting that go into production. One of our customers nearly went into production with something that was hard-coded to someone's home directory. That was nearly a massive embarrassment for them because, of course, that build would not have run elsewhere. It was a lesson in clean test environments, as well as a lesson in other areas, but very pleased to have found that and fixed that for people, for them. We look at sets of small files, large files. They can cause problems for file systems. Shared log files, absolute disaster for running at scale, as well as old and slow libraries and binaries. This is just a screenshot showing you some of the other things that you can check. These are some things that we look for, but it's up to you what you look for. We look at the reads, how long they take, whether they failed. We look at small reads, writes, seeks. That's a really good way of picking up random access as well. We've seen applications actually read very, very large files backwards. The performance implications of that are absolutely horrendous and completely unnecessary. This is a... so I'm now going to show you some of the data we found from other applications. This is a genome pipeline, and it uses a library called R, very sensible, very, very, very widely used in the industry, and a completely vanilla call read.table actually does single byte reads. This particular application does more than 500,000 one-byte reads per second. We've seen way over 1 million one-byte reads per second. Absolute disaster for any file systems. This is an application that is very, very small and not actually very I/O intensive, but run very often. I've had to censor the data here so that you can't identify the customer. But essentially what's going on here is this is a timeline view from our application. Each one of these bars is a process. This is the main process, and this is a list of what it's doing. Read file info, so that's reading metadata, so ownership, existence of files, and so on, and anything read is a failure. What it's doing is every time it runs, it opens a set of config files, and it searches something like a path variable to find those config files. Now, the path variable has been set up the wrong way round with a whole bunch of different locations appended during this setup process here, which is a whole hierarchy of scripted infrastructure that they've put into place to automate this particular application, and it's trawling the file system, looking for this file and trying to test the existence and open it. And actually, this it runs for 6 minutes. And the failure covered quite a large part of the first minute of running this application. We managed to speed up the application by 10% by changing the path variable to be prefixed instead of appended. So these things really, really, really important. Again, this is another metadata example. This is an application that creates lots of small files. That architecturally is a bit of a disaster, but it's very, very hard to rewrite this application, so you've just got to plan for it. And that's fine. Only after a while, they realized, because they profile regularly, that the number of metadata operations, so these are stat operations, checking the existence of a file, was dramatically increasing. And what had happened is someone had added a progress bar. They knew they were creating lots and lots of files, and they measured the progress of the application just by statting how many were there. So as you can see, total disaster from a metadata point of view. Just thousands and thousands of, tens of thousands of IOPS that are completely unnecessary. And to prove that we do this too, this is actually a graph from our test framework. And at some point here, we actually did some optimizations in our product. And we saw this particular test 32, increase in performance quite dramatically. Now, because we monitor that, we now know this. So this was a side effect. This wasn't the goal of the particular piece of work, but because we monitor that and because we look at historic performance data for the I/O for this particular test, we know that the performance has improved, and we now can reduce our tolerances in the performance acceptance tests. Now, if we hadn't done that, we could easily have seen a regression in the performance of this test, and or we wouldn't have seen it, rather. It could easily have happened and we wouldn't have noticed, because the acceptance test would still have passed, and we'd have lost that really, really important performance increase. So, so yeah, we're happy to, that we practice what we preach on in that particular example. You can't talk about I/O without talking about Meltdown and Spectre. So one of our customers estimate that they've seen more than a 13% overall slowdown, because they've got quite I/O intensive applications, and for them that means a reduction by more than $15 million in effective compute capacity per year. So very, very expensive. The reason that's a problem is because, so the patches for Meltdown and Spectre cause I/O operations to become very, very expensive, because I/O operations involve a switch from user space into kernel space. And the patch for Meltdown and Spectre means you have to flush all your memory lookup caches whenever you do that. So from that point of view, it really puts those 1-byte reads and those metadata operations into perspective. Anything you can do to avoid I/O and keep it all in user space for as long as possible is really going to help you when mitigating the effects of the Meltdown and Spectre bugs, which are going to be around for a really long time. Obviously, something that you've got to measure. Not all hardware will be affected. Some hardware already has got separate caches for user space and kernel space, in which case the effects, the performance degradation will be minimal, but only you can tell that. So finally, I/O profiling as a service has really got kind of 3 keystones. So one of them is continuous monitoring, so that you can see what you're doing, what your baseline should be, what's good and what's bad. The next one is regression testing to make sure that you always improve your I/O. And the third one is developer opt-in, so that they can get more information really, really easily in a really easy to absorb way that's relevant for their application. So good I/O is not about making sure that everything is good all the time. It's about making sure that that low-hanging fruit, the stuff that really matters, the stuff that's going to one day crash your system, making sure that you've got a handle on that. So I said I'd talk a bit more about our products at the end. So Breeze is the tool that we did most of the analysis with in a lot of detail. It's not really suitable for running at enormous scale, because it does gather a lot of information. It's really good for dependency analysis, really, really good for cloud migration when you're doing that lift and shift and kind of legacy discovery. And it, as I say, it gives you a kind of a report to start from that gives you an overview of what we think the major issues are going to be for your application before you can zoom in and see a bit more information if that's what you want. Mistral is the tool that we deploy at scale when we want to measure thousands and thousands of applications all at once. And that's the one that you'd integrate with your CloudWatch, with Elasticsearch and Grafana and so on, to really get a historic overview of what's going on. There are a whole bunch of other tools you can tap in to get other information if you want, and this is I just love this picture. I stole it from a guy, Gregg. He's a genius, and he's done a lot of work on what kind of tools are available in Linux. Most of this is really nothing you want to touch unless you're tuning for a very specific application. But I recommend, if you Google his name, you'll come up with a blog that really goes into detail on a lot of these different tools. So yeah, really, really useful tools for tracking all kinds of I/O at all kinds of levels. So, 6 minutes early. That's 6 minutes of beer time, potentially, depending on how many difficult questions you want to ask me. But that's a sort of a very whistle-stop tour of I/O and what kinds of things can be done. Thank you very much.